Okay, we've just started recording, so I'll do the introduction. Welcome to the Airsea Fluxes from Space webinar series. Today, we're fortunate to have Luna Bai, who's a fourth-year graduate student at Caltech. She's going to talk about sub-mesoscale wind front interactions and their impact on ocean vertical velocities. And Luna is thinking about graduating, and so on the lookout for a postdoc if anybody has ideas for her. So go ahead, Luna.
Thank you for the intro, Sarah. I will start sharing my screen. Okay, sorry, I just followed my second slides. Okay, cool.
Looks good.
Awesome, thank you. Yeah, I'm really excited to be here to talk about our research to the Oasis crowd. So again, I'm Luna, and these are my advisors and collaborators. And today we're going to be talking about wind front interactions and some ocean vertical velocity work that we did. And a spoiler alert is the main part of the talk is going to be work that we did with a high resolution coupled ocean atmospheric simulation. And at the very end of the talk, we're going to show a little bit of the ongoing work that we did with ocean vertical velocities in situ environments with S-mode Doppler scat data. Cool. So first, I want to motivate on what exactly is wind front interactions. So I think for a really long time, when people think about the relationship between atmosphere and the ocean, they always think it's a one-way relationship, which is the atmosphere drives the ocean, or the ocean is more or less a passive receiver. But in the starting from the past 2 decades, with the advancements with satellite observations and more understanding of mesoscale eddies, people start to think, hey, that might not be the case. And ocean eddies, especially mesoscale eddies, might have an impact on the atmosphere. And so here is a example study by Charlton and Xie 2010. And so on the left, plotted the color map is showing the wind thrust curl, and the contours overlaid are the crosswind SST gradients. And just by looking at it, we can see there's this really strong spatial correlation between these two. And indeed, when this information has been collapsed into a 1D thermal feedback plot, which has crosswind SST gradient bins on the x-axis, and the mean values of wind thrust curl on the y-axis, we can see this strongly positive correlation between those two. And so this suggests that ocean surface features, in this case, SST gradients, would have an impact and can imprint their own features on the atmosphere. So is there any other surface ocean features that can impact the atmosphere? And here is an example study by Leonard et al. 2016. And so this is a numerical simulation. And on the left is a snapshot of their ocean surface vorticity. And I can't find a plot for the wind thrust curl, but if there were one, we should be able to see that they're also highly spatially correlated. And if we do a 1D current feedback, or a 1D analysis with vorticity bins on the x-axis and mean values of wind thrust curls on the y-axis, we can see that these two are also highly correlated, but now they're correlated in a negative sense. So there's actually a rich pool of studies that have looked into either current feedback or thermal feedback individually. But in the real ocean, a lot of times the strong SST gradients can be correlated with strong velocities and velocity gradients. And so is it possible that these two feedbacks could interact or contaminate with each other? So here is a study that we led in our group about the joint impact of the thermal and current feedback. And so in this study, we explored a very energetic region in the Southern Ocean. And our main result is called this 2D feedback, concentrated on the wind thrust curl. And so this is called a 2D feedback because instead of only having one axis, now we have two. We have crosswind SST gradient on the x-axis, and we have ocean surface vorticity on the y-axis. And now the color bar is showing the mean value of wind thrust curl occurring at some combination of the crosswind SSD gradient and ocean surface vorticity. And so we can see that it has a very specific distribution. We have the zero line, but it's tilted in this way. And we have negative values here and positive values here. So how should we understand what's going on here? So if we look at the schematics on the right, imagine that if we only have current feedback, i.e. we only have ocean surface vorticity on the y-axis, but now we have something irrelevant to wind stress curl on the x-axis. And because we know from previous studies that vorticity and wind stress curl are negatively correlated, so we would expect to see negative wind stress curl at positive vorticity. And the same thing for the thermal feedback. If we only have crosswind SST gradient on the x-axis, because of their positive correlation, we expect to see positive wind stress curl at positive SST gradient. And now imagine that we're adding those two blocks together. So in the first and third quadrants, where the impact of these two feedbacks are actually counteracting with each other, we can see that they're actually canceling off each other's impact. And at some point, this cancellation is complete. And so we see this zero line in the middle. But in the second and fourth quadrants, current and thermal feedback's impact on wind stress curl are actually reinforcing on each other. And so these are the parameter space that we would expect to see the strongest and most anomalous values of the wind stress curl. And that's exactly what we're seeing here in this plot. And so this suggests that current and thermal feedback are actually working together or working in tandem to modify features in the wind stress curl. And they have this interaction of reinforcing each other or canceling each other's effect. And so we also did this 2D feedback on the wind stress divergence. And so for wind stress divergence, now it's being correlated with downwind SST gradient and ocean surface divergence. And we can see that it basically has the same sense of what's happening with the wind stress curl. We also have this tilted zero line, and so this also suggests that wind stress divergence is positively correlated with SST gradient and negatively correlated with ocean surface divergence. And these two are also working together to modify small features in the wind stress divergence. And so wind stress divergence is of great importance to the atmospheric side because they could potentially modify or induce vertical velocities and modify structures in the atmospheric boundary layer. But in our study, or in the study that I'm going to talk about, we're going to focus primarily on the wind stress curl. And so to the right is a very recent study by Kanahiro et al. 2014. And so they, in their super high resolution, even higher resolution numerical simulation, they also conducted this 2D feedback analysis, and they also find this tilted zero line and between wind stress curl and ocean surface vorticity and crosswind SST gradient. So this is very reassuring, which means that this mechanism is not model dependent. And in addition to that, they also divide this plot into different 4 quadrants, and they calculated the linear correlation coefficient between crosswind SST gradient or ocean surface vorticity with the wind stress curl. And so they further prove quantitatively that in the first and third quadrants, these correlation coefficients are a lot smaller compared with the fourth and second quadrants, in which the two effects are reinforcing each other. Oops. Oh, okay. So for the previous studies, or in these previous studies, it has been shown that ocean surface features, in this case, SST gradient and ocean surface vorticity or velocity gradients, can have an impact on the atmospheric field or the atmospheric wind field. But that is only one of the 2 links in a wind front interaction. So ocean impacts the atmosphere, but what about the atmosphere back to the ocean? So how would the impacted atmospheric wind fields in turn modify the ocean surface dynamics? And because we focus on the wind stress curl, a natural starting point for us to look at is the surface wind-driven ECMA layer. And so here are just two random schematics of the surface Ekman layer. And so we can see the wind is blowing this way. And if we're on the northern hemisphere, the surface current is 45 degrees to the right of the wind, and there's this integrated Ekman transport. And then because of convergence or divergence of these surface winds and Ekman transport, we would have induced Ekman vertical velocities. And so these equations are from Galb et al. 2015. And so these represent the total Ekman vertical velocities. And we can see if we take the curl for these two parts, they split into two components. One is the linear Ekman vertical velocity, and the second one is a nonlinear Ekman vertical velocity. So for a really long time, when I was first learning physical oceanography and everything, the linear Ekman vertical velocity is the only Ekman vertical velocity that I was taught. But then now if we do this curl properly, we can see that if we do the curl for 1 over f plus theta, we can recover the second term. And this part is related to the gradient of ocean surface vorticity. And this is called the nonlinear Ekman vertical velocity. And so there's previous studies that have looked into all these different vertical velocities. So here is a study, a numerical study by Seo et al. 2016. So here is along the coast of California. And they split the linear Ekman vertical velocity into an SST-induced part and a current-induced part that I'm going to talk about in detail later. And then in the middle is the nonlinear Ekman vertical velocity. I think the main takeaway from this study is these current or thermal feedback induced Ekman vertical velocities can be as important as vertical velocities caused by internal ocean dynamics, such as baroclinic instabilities. And so these vertical velocities are also of great importance, and we have to take into account of them. But then just by more specifically looking at this figure, they conclude that in this case, the current feedback is of similar magnitude to the SST-induced vertical velocities, but a little bit stronger. But for the nonlinear vertical velocities, in this case, it's just a lot smaller compared with the SST-induced one or the current-induced one. And here is a plot from Galb et al. 2015. And so they are also looking at the SST-induced and current-induced velocities. And here is a global ratio of those two. And we can see that in general, we can see like patches, red or like yellow patches in the middle of these gyres. And I think these represents like a little bit less energetic regions. So maybe SST-induced feedback would be a little stronger. So the ratio would be larger than 1. But in the rest part of the ocean, especially in the Southern Ocean or in the more energetic region or in the boundary currents, the ratio is slanted towards the current-induced Ekman velocity, so they would be a little bit stronger. And so in our study, we want to do two things. The first is we want to revalidate or our previous study, the 2D feedback calculations in a different dynamical regime. So we also chose the eastern boundary current, the California current system. And then second, we want to look at a series of these Ekman vertical velocity calculations in a higher resolution simulation. And we just want to see if there's anything new that pops up, and we want to compare with these previous pioneering studies. And so what we're going to do is we're using this super high resolution global air-sea coupled simulation. It has an ocean part and an atmospheric part. And there's information exchange between them to ensure that there's a good coupling. And for the ocean part, the horizontal resolution is about 2 to 4 kilometers. But in the California current system that we're looking at, the resolution is about 4 kilometers. Cool. And so we would be interested in looking at different spatial scales. So the first thing we did is a spatial filtering for all of the fields that we're going to be working on. And so we are exclusively going to be focusing on the April data. And so here we have 2 panels, 6 panels, but 2 columns or 2 rows. So the first row is the ocean surface vorticity, and the bottom row is the crosswind SST gradient. And so we're showing the full fields, which are not filtered at all, which is just like taken directly from the simulation and calculated it. And then we're filtering every single field to be 30 to 200 kilometer, and we call this like larger scale or mesoscale. And then everything smaller than 30 kilometer that we kept is called smaller scale or sub-mesoscale. And similarly, we also did this filtering for the atmospheric winds. So on the top row, we have the tau x, and in the bottom row, we have the tau y. And if we pay attention to the magnitude of these filtered or non-filtered tau x and tau y, we can see that the unfiltered tau x and tau y are an order of magnitude stronger than the mesoscale tau x and the sub-mesoscale tau x and tau y. And I guess this is not very surprising because tau x and tau y, these atmospheric fields are like very large scale, but this would come up later in our calculations. And I forgot to mention this black box here is the location of where the NASA S-mode in situ experiments are happening, which we're going to do more detailed 2D analysis in this black boxed region. And then we're also going to compare some of the S-mode observations with what's happening in the LLC data in this region. Cool. And so the first thing we did, oops, sorry, that was my Siri. So the first thing we did is to look at or to redo our 2D feedback calculation. And so because we did this filtering, again, we looked at it at mesoscale on the left and sub-mesoscale on the right. This is exclusively for the data inside the black box, and this is in April. And so we see that there's this tilt to zero line happening at both mesoscale and sub-mesoscale, which suggests that this 2D feedback or this joint impact, this joint control between current and thermal feedback on the wind thrust curl is happening at both mesoscale and sub-mesoscale. But large anomalous values of the wind thrust curl is only showing up or is only present at sub-mesoscale. And this is not quite surprising because at sub-mesoscale resolution, we are expecting to see more crosswind SST gradient or stronger SST gradient and stronger velocity gradient. So that's why we're seeing these really large and anomalous values of these wind thrust curl. And so that was very reassuring. We recovered these 2D feedback in a much less energetic eastern boundary current region. And so the next thing we want to do is to calculate Ekman vertical velocities. And basically we have two main goals. The first goal is to calculate to do these calculations at different spatial scales. That is why we did all those spatial filtering. So we want to calculate these at meso and sub-mesoscale or larger and smaller spatial scales and try to compare if there's any magnitude difference or if there are distributions, if there's any difference. And then the second main thing that we want to do is to somehow we want to isolate the current induced or the SST induced components for both the linear and nonlinear Ekman vertical velocities. So we just want to see the individual contribution for the SST or the current induced feedbacks and their impact on the vertical velocities. And we see by from all those previous studies, we can see that this can be done for the linear Ekman vertical velocity. And it's kind of straightforward because for the formulation within the linear Ekman vertical velocity, there's this wind thrust curl component that pops up. And then because we know this correlations between the crosswind SST gradient and ocean surface vorticity with this wind thrust curl, we can approximate this wind thrust curl by ocean surface fields. So for example, for the SST-induced linear Ekman vertical velocity, for the part on top, we can approximate this part of the wind thrust curl with crosswind SST gradient multiplied with a constant. And this constant is the correlation coefficient between the crosswind SST gradient and the wind stress curl. So this is representing what SST or surface temperature gradients is contributing to the linear equinovertical velocity. And similarly, we can also do the same thing for the current induced equinovertical velocity. And instead of having the full wind stress curl, we're approximating this wind stress curl with ocean surface vorticity and another constant. However, things becomes a little trickier when we want to do the same thing for the nonlinear equinovertical velocity, because if we look at the formulation here, there's no wind stress curl that pops up, but instead there's only tau x and tau y. And tau x and tau y can be a little tricky because we know that current and thermal feedback, they are correlated or they can modify the wind stress curl. So they are definitely also modifying the tau x and tau y. But to directly see this correlation or to directly separate tau x change into SST-induced change or current-induced change is not very straightforward. And so when in doubt, you do an integration by parts and see what happens. And so what we're doing is we're pulling in this tau x and tau y factors into these derivatives. And so now instead of having these two terms that is solely like modified by this tau x and tau y that we're unsure to deal with, now we have three terms. So the first two terms, again, are still impacted by this tau x and tau y, but now we have a third term, and this third term magically pops out to be the curl of tau or the wind stress curl. And then we can at least approximate part of this wind stress curl into a current-induced component and the SST-induced component that we can try to quantify. So in our in the plots that I'm going to show below, we are actually doing these. Again, for the SST-induced and current-induced linear equinovertical velocities, we're approximating them with surface ocean fields multiplied with their correlation coefficient with the wind stress curl. And for the nonlinear component, for the first two terms, we are still using tau x and tau y coming from the atmospheric fields. But then because of this massaging of the equations, this wind stress curl pop out. And so we are approximating this wind stress curl also with surface ocean fields to represent some of the effects coming from surface currents and surface SST gradients. And so here are how those vertical velocities look at mesoscale, which is the top row, and sub-mesoscale, which is at the bottom row. And so if we, so the top row, which is about 30 to 200 kilometer resolution, can be compared more straightforwardly with previous studies. And so we can see that the magnitude for the SST-induced and current-induced linear equinovertical velocities are pretty similar. Maybe the SST-induced vertical velocities is a little bit stronger. But they are, the main message here is the nonlinear equinovertical velocity at mesoscale is just so much smaller compared with the current and SST one. And this is very consistent with what we found in, or like what we read about in the previous studies. But now when we move to a sub-mesoscale, we move to smaller scales, we can see that maybe the magnitude of the SST-induced and current-induced linear vertical velocities are still pretty comparable to each other, but we can clearly see that the magnitude of the current-induced vertical velocity is picking up, or is becoming stronger compared with the other two components. And for the nonlinear equinovertical velocity, it's actually a lot stronger at the mesoscale. So even though it's pretty negligible or pretty small at mesoscale, at sub-mesoscale, it's becoming comparable with the other two components of the linear equinovertical velocities, and is no longer a less dominant contribution. And so following Gallup et al. 2015, we are also curious about the ratio of this SST-induced and current-induced equinovertical velocities. And so on the left, we are showing these ratio on the mesoscale, and on the right, we're showing these ratios of mesoscale, or scales smaller than 30 kilometers. And we can see that at mesoscale, it's clearly very, so everything red, it means SST is dominating, or everything blue or green is showing the current is dominating. So we can see that at mesoscale, it is clearly very large scale SST dominated, no matter if it's offshore or if it's along the coast. But then as we move to smaller spatial scales, we can see that current induced econovertical velocities are start to picking up, especially along the coast. And I think this is also not too surprising because the current induced vertical velocities is also related with the ocean surface vorticity, and at smaller spatial scales, we would expect to see a lot stronger vorticity coming through. Cool. And so that was for the separation of the linear econovertical velocity into current and SST-induced components. Then what about the very tricky nonlinear econovertical velocities? And so here at the very bottom, just to remind you, this is the formulation that we're calculating right now. This is after we did the integration by parts. And so I color coded it just so it's easier to see for the blue part here, because these two terms still contains the tau x and tau y that still can't be separated into current induced or SST induced components. So we're lumping them together and we call them wind stress induced nonlinear econovertical velocity. And the green part here is current induced and the red part here is SST induced. And so on the top row, we are computing all of those fields with the unfiltered fields or the full fields. And so we can see that at every scale, or like just in the simulation, the nonlinear econovertical velocities are very much dominated by wind stress induced components. So the first two components that's involving this tau x and tau y is very, very big. And also this is not very surprising because if you recall the tau x and tau y snapshots that we showed before, they are very strong, especially at unfiltered scale. And so even though they're modified by ocean surface vorticity here, but if we take a gradient of those, they are still very strong both along the coast and offshore. And at full scale, current induced and SST induced nonlinear econovertical velocities are of an order of magnitude smaller compared with the wind stress induced one, especially for the SST induced vertical velocities. It's just pretty much negligible. But now, as we move to smaller than 30 kilometer scales, we can start to see that things begin to change. So for the first two terms, which is wind stress-induced nonlinear econovertical velocities, they become very, very small and very negligible. And this is because tau x and tau y at smaller spatial scales become very small, or their magnitude become very small. But instead, for the current-induced component at sub-mesoscale or smaller than 30 kilometer scale, it is as strong as it is for the full scale. And now it is becoming the dominant component, or becoming dominant contribution to variabilities and magnitudes of this nonlinear econovertical velocity at sub-mesoscale. But then for SST-induced econovertical velocities, it still remains very small and very negligible. And so I think the lessons that we learn here is at very large scales, or at very large unfiltered scales, it is actually the surface wind stress that's making the dominant contribution to this nonlinear econovertical velocities. But as we go to smaller and smaller spatial scales, the atmospheric impact on this nonlinear econovertical velocity is drastically decreasing. And it is actually the surface currents that's picking up this, this dominance and this contribution to the nonlinear econovertical velocity. So before I showed all those fields in the spatial sense, but then we are also interested in their net contribution in a specific area. So if they're contributing to a net upwelling, or if they're contributing to a net downwelling. And so here we are showing the time series of the domain average all sorts of vertical velocities induced at different spatial scales. And so this is, we are focusing on, again, the black box region again, which is the S mode region. And so we can see that for SST-induced linear Ekman vertical velocities, it is actually the mesoscale that's dominating, and the sub-mesoscale one makes for a subdominant contribution. But for both nonlinear and for current-induced linear Ekman vertical velocities, it is actually the sub-mesoscale that is making the dominant contribution, that is overpowering the mesoscale contribution. And what about if we look at just mesoscale or sub-mesoscale for all of these vertical velocities adding together? And so mesoscale, so we can see that this time series is actually mimicking a lot to the SST-induced linear Ekman vertical velocity time series. And that's not quite surprising because we know that at the mesoscale, it is actually the SST-induced vertical velocities that's dominating. But the mesoscale nonlinear and mesoscale current-induced linear are very small or of secondary importance. But it becomes very interesting if we look at some mesoscale. So before, if we look at some mesoscale, we would expect the nonlinear component or the current-induced component would pick up or would make at least a very net strong contribution at some mesoscale, but we wouldn't expect the SST to make a dominant contribution. But for some reason, the sub-mesoscale component for the nonlinear Ekman vertical velocity and for the current-induced linear vertical velocity, the domain average is actually canceling off with each other. And so, in fact, sub-mesoscale motions is not making a very huge contribution in terms of a domain average or in terms of a net domain mean. And so if we add all of the 80 scales together, which is mesoscale plus the mesoscale, it is also not too surprising to see that it is actually the mesoscale SST-induced linear Ekman vertical velocities is dominating everything. And so for a conclusion for what we learned in the LLC simulation or in the coupled simulation, the first thing is we're able to recover this 2D feedback in the eastern boundary currents. And we also find that large anomalous values of the wind stress curl are only generated at some mesoscale or smaller than 30 kilometer scale. And in April, which is the month that we are examining in this study right now, the SST and current-induced linear Ekman vertical velocities and mesoscale have large magnitudes, are pretty similar, but the sub-mesoscale current-induced Ekman vertical velocities contribute to a large positive spatial average, at least in a time average, or at least in a time series sense. And nonlinear Ekman vertical velocities are stronger and uniformly more negative at sub-mesoscale. And this sub-mesoscale contribution mainly comes from the current-induced component instead of the SST-induced or the wind stress-induced part. But overall, mesoscale SST-induced Ekman velocities make the dominant domain average or net contribution to these vertical velocities, and so we suspect that they could also dominate either the dominate most of the vertical fluxes that could be caused by these Ekman vertical velocities. Cool. So that was a temporary conclusion for our results in the LLC model. And if there's not burning questions right now, I would like to continue to finish the last little bit of the analysis that we're doing with the S-mode simulation. And then if there's questions about these, I'm happy to answer them. And also the page number is at the bottom corner. So if you have some questions, you can just point me to the page and we can quickly go back to it. Cool. So what we're doing right now, it's still very, very ongoing. It's still very preliminary. Is we're looking at some of the observational data from these S-mode experiments. So S-mode stands for Sub-mesoscale Ocean Dynamics Experiment. And so we can see these are some configuration plots that I found online. So on the left, we can see all of these various instruments I found. And it's actually very amazing that every time when I hear a S-mode talk, there's new instruments popping out that I wasn't aware of. And it's just very amazing how much data we have in this region of the ocean. But then this talk, we're gonna focus on the data coming from Doppler scat. So Doppler scat is a scatterometer, and I'm not an expert on it, but to my understanding, what Doppler scat is doing is, so if winds blows by across a part of the ocean, it will onset some capillary waves. And so this Doppler scat, or this scatterometer, is able to detect these capillary waves and is able to transform this information into some sense of a relative wind stress between the atmospheric stress and the ocean surface velocity. And then from this wind stress, we can then back out into what's the relative velocity between the platform, the surface, and this neutral wind stress between the atmosphere and the ocean. And the really cool thing about these Doppler scat measurements is it can have the simultaneous measurements of surface vector currents and surface winds. And this is super exciting because for wind stress interaction studies, we really want co-located and simultaneous measurements for all of these quantities as much as possible. Cool. And so here are some very, again, preliminary results that we recovered from Doppler scat. So the date is October the 26th in 2022. So this is in their IOP, in their IOP1. And then, so for everything I'm showing here, I'm applying a smoothing scale of about 2 kilometers. And so, so I'm showing 3 fields here. On the left is the crosswind SST gradient. This is not coming from Doppler scat, sadly. This is actually from a satellite data that we find to be at around the same time with this Doppler scat measurements. And then the middle and the right panel is showing the ocean surface vorticity and showing the surface wind stress curl measured by Doppler scat. And we kind of boxed up these whole domain into 2 main parts. So the horizontal box represents a more persistent frontal feature that we find. So it's slowly evolving, but it doesn't. You can retrieve a timing of it. It's not very transient. But for the vertical box to the right, we can see that you can see lots of fingers going on. And if you look at the satellite data, you can see actually they are like evolving very quickly, and there are some transient frontal features that we can see. But then just by looking at these vorticity and the wind stress curl calculations, we can already see some of the negative correlation between those two. And this is very exciting. And then between the crosswind SST gradients and the wind stress curl, we can already see some positive spatial correlations between those two. And because we are very interested in the Ekman vertical velocities, so here are the linear to the left and nonlinear to the right Ekman vertical velocities that we calculated with the wind stress curl from Doppler scat data. And as you can see, for the nonlinear Ekman vertical velocities, it's actually quite noisy. Right now, is this because I'm taking the gradient of the velocities, and so there's more smoothing, there's more cleanup that I need to do. But if we just look at the general features of what's going on, so for the linear Ekman vertical velocity, this is a snapshot. We can see that the magnitude of it is a lot stronger than at least what we see in the LLC simulation. But then the structure or the distribution of this linear Ekman vertical velocity is very consistent with the structure of what we see from the wind stress curl, or like a reverse structure of the vorticity. And this is not very surprising because this linear Ekman vertical velocity is pretty much dominated by these wind stress curl. But for the nonlinear Ekman vertical velocity, because it is dominated or somewhat related to these surface vorticity gradients, so we can see that in the area where we have those persistent frontal features, we actually don't see huge nonlinear Ekman vertical velocities, but instead we see very large nonlinear Ekman velocities happening at those very transient frontal regions where we would expect to see so much stronger the ocean surface vorticity gradients. And just for comparison, So this is what we have from the high resolution coupled simulation that we're using. And so this is from November the 1st, at midnight, November the 1st. And again, we calculated the linear and nonlinear incremental vertical velocities. And so first thing we see is it's a lot coarser because the resolution is not as high. And then we can see that there's actually some really high spatial correspondence between linear and nonlinear incremental velocities in the simulation that I don't quite have a good idea of why right now. But again, we can see the magnitude of these either the linear or the nonlinear incremental vertical velocities are greatly reduced compared with what we see in Doppler scat observations. And lastly is just some histogram for what we're seeing for both of the incremental vertical velocities in Doppler scat and in the simulation. We can see that in general, the distribution or the skewness of these two vertical velocities in these two environments are actually pretty similar, especially for the linear incremental vertical velocities. So we see they are skewed to the right, which is they have a longer tail on the positive ends. But for the magnitude of what we see in Doppler scat and for the LSC simulations for these vertical velocities, the Doppler scat observations are just 4 or 5 times stronger than what we can recover from the LSC simulations. And so this also tells us that in the LSC simulations, we are probably also missing some dynamics, which is also hitting to our future goal for the LSC simulation study is we want to look at a much higher resolution regional simulation to be able to redo these calculations at even higher resolution or even smaller spatial scales to see if there's anything that we missed for the dynamics for the nonlinear or the linear incremental vertical velocities. And that's it. Thank you for listening. And sorry for asking you guys to holding off the questions. I'm happy to answer any questions.
Well, thank you. I see that Dudley has his hand out, and then we'll let Dudley go, and then Amit Tandon has a question in the chat.
Cool.
Hi, thanks for that very nice talk. It's a nice extensions down to small scales of things that I've looked at a while back in the past. There's one thing that I want to mention, and that is that what you call the nonlinear vertical velocity is a theoretical concept, and it dates back to by Melvin Stern in 1965. There are some assumptions in that paper about in order to get that equation, and one of those assumptions is that surface current vorticity is small compared with the planetary vorticity. And when you get down to those really small scales that you're looking at below 30 kilometers, that's probably not true. It's not a lot smaller, and in some places it's probably bigger. And so it's always been a little unclear to me how relevant the nonlinear Ekman velocity, vertical velocity really is. The only way really to resolve this is to compare the vertical velocities that you calculate on those small scales with vertical velocities calculated directly from either the model or the S-mode data. So do you have plans to look at that in the future to figure out how legitimate the nonlinear vertical velocity is?
Yeah, thank you. That was a really, really good question. So actually, we were also trying to compare what we've been calculating to what we see directly in the model simulation, and hopefully for the Doppler scat data. And a very tricky part is in the model, the vertical velocity fields are hugely dominated by waves. And so we see these oscillating positive negative patches for the vertical velocity fields. And so I think one of our collaborators, so Hector, he has a really nice paper about a simple way of trying to separate the wave component out of the vertical velocity fields. And so that's what we've been trying to proceed. And so yeah, we would be very excited to compare our incremental vertical velocities calculations with what we see in the model, but just we have to think of a safe and legitimate way to remove all of those wave features that we see in the simulation. And I think the same thing would apply to what we see in the S-mode observations too.
A few years ago, I did those calculations from a different model, a much simpler model that didn't have those small scale wave processes and things in it. And there were patterns in the vertical velocity calculated from the near surface divergence field that look qualitatively similar to what you calculate for the nonlinear Ekman vertical velocity. But when you actually overlaid them and tried to correlate them, it was pretty disappointing. So I hope you have better success than I did.
Thank you. We actually did like a very small checkup in the Southern Ocean, and I think, as you said, there is somewhat like a spatial offset for features of the like vorticity fields or like the vertical velocities in the model with the Ekman vertical velocities that we calculated. But yeah, but if somehow we can account for or physically explain why there's a spatial offset, I think it could be something.
Yeah, there's some more work to be done there.
Yep.
Look forward to seeing what we come up with.
Thank you.
Okay, next, Amit has a question in the chat. Amit, do you want to unmute and ask?
Sure, I can go ahead. Thank you for a very nice talk, Luna. I enjoyed it.
Thank you.
My question is very much probably in the same vein as Dudley. The expression that you showed us for the nonlinear Ekman, right? I mean, the curl tower, rho f plus zeta.
Yep.
Again, same reference. Also is assuming sort of nearly steady state or low frequency flows. And yet we know that the sub-mesoscales are actually very time dependent, to have a strong near inertial component. So when you're saying you're going to do this for the month of April, how does that analysis take into account the influence of the time dependence, particularly the near inertial flows? And then, there was a paper that Amla and I wrote way back when, and we tried to look at what a 3D nonlinear simulation was doing versus what the nonlinear W was looking like. And we could see lots of matching for the downwelling, but not for the upwelling. The upwelling seemed to have more than just nonlinear Ekman. And at the time, I thought it had something to do with the time dependence, but or mixing. So I'm curious to hear about those.
Yeah, that's also a very good question. And I think I have not thought about like this transient or like the transient or like time non-stable influence or like the near inertial influence to these calculations that much yet.
Right, because there's an omega plus f that'll come in. If you think about the partial t term, that's going to give you another sort of quasi, and that's, and so once you get this f plus minus omega, with omega getting closer to f, then you'll get other terms beyond what you have. And I think it's I'm a little concerned that when we start doing these with instantaneous snapshots, and this is just not for a comment for you, but in general, is, if we have snapshots of fields and we start doing these with snapshots, then it's not clear to me how much we are looking at the, what the unsteady effects are versus applying these formally, which actually apply to low frequency flows. And as Dudley said, to cases where zeta is not particularly small. So we have to be careful about where we are applying these.
Yeah, that's a really good point. So for the results that I showed in the simulation, we were doing it for the snapshots, but we tried to take into account some of the time variation by doing like a temporal average or like monthly averages, and we can do even longer things. So I think for, especially at mesoscale, for these low frequency impact of these vertical velocities, I think those could be very or more robust compared with what's happening more transiently or more at the mesoscale. For the Doppler scatter observations, it's a little tricky. Sorry, because there's only a couple snapshots that's available to me right now, or like there's only a couple snapshots. I would be very excited to see if there's any way I can try to combine those snapshots together to make sense of more of, as you said, a low frequency or a slowly varying motions result for what's happening in terms of the linear and nonlinear Ekman vertical velocities. Sorry. But yeah, I think that's, yeah, it's just, it would be more exciting if we could have these Doppler scat sort of measurements, even at like bigger areas or even at longer periods, so that we can look at these different things together, both at like shorter snapshots timescales or at longer monthly or yearly averages.
Thank you.
Yeah, thank you for the question.
Other questions for Luna? I wanted to ask about the resolution question you raised. So one question for resolution is that the atmosphere and ocean in the LLC model are at different resolutions. Do you think that that makes a difference? Should the atmospheric resolution ideally match the ocean, or does that mismatch not pose a problem?
Yeah, so that's a very good point. So for the LLC simulations, the one that I'm using right now, the ocean is at 2 to 4 kilometer resolution, but the atmosphere is at a 6 kilometer resolution. And so I think Ray has a paper about like the different resolutions for the atmospheric simulation and different resolutions for the ocean simulation. And there could be some, because we have to essentially interpolating the atmospheric fields onto the ocean grades and the ocean fields onto the atmospheric grades. So there's some, I think there's some energy leakage if we're doing these for different spatial scales. Mm-hmm. So ideally, it would be great if we could have the ocean side and the atmospheric side to be of the same resolution. Mm-hmm. But and I think that's what the model developer in JPL, like Dimitri, is trying to pushing for. But cheap. In our calculation, yeah, definitely not cheap. I think for one of the thinking that they have is because atmosphere is considered more like a larger scale or something, so it could be useful and cheaper for them to keep the atmospheric grids at a larger or like a sparser grids than the ocean side. But ideally, I think for the most accurate representation, it would be great if we could have them on the same grades at the same resolution. But I think for the I think in the general part, especially if we're doing like somewhat a large spatial averages, hopefully it's not causing a lot of issues for the calculations that we're doing because of this grid resolution difference.
Thanks. I see that Roger has his hand up.
Thank you.
Well, thanks for a nice talk. Very interesting, Luna.
Thank you.
I was intrigued by what seemed to be that rectification effect from the term after you did the partial integration, the term from the Ekman pumping that had the product of the vorticity and the relative vorticity-driven wind stress curl, which then is, in approximation proportional to the vorticity. So this becomes the correlation coefficient times the square of the vorticity. And it seemed like you didn't emphasize that, but I wonder if you thought about that anymore and whether you can, just assume some random fields and derive that rectification directly from the original expression and get some sort of estimate of how large it is. Because if it's, a persistent term, it may have some effect, even though it's relatively small and hard to see. Do you see what I mean?
Yeah.
If you go back to for instance, if you go back to the slide that had some of those fields on it, that particular term is all blue.
Yeah.
Yeah, right.
Part,
So
yeah.
the third panel's third column. Yeah.
Yeah. That's a very good point, because as you said, so this wind stress curl coming from the current induced components, we can approximate it as like alpha times with vorticity. And so this whole term just becomes alpha times vorticity squared. And if alpha is like a negative, because the correlation between vorticity and wind stress curl is negative, so that's why I guess predominantly we're seeing this term to be negative. And I think that could also explain why this term, this sub-mesoscale component of this current-induced nonlinear economic vertical velocity, if we look at it in this average sense, it's kind of mirroring the contribution coming from the current-induced linear economic vertical velocity, because they scale very similarly. But in terms of like trying to back out this rectification term, we have not thought about it that carefully. But if you have any ideas, we really welcome for any ideas or insights about those.
Okay, great. Thank you.
Thank you.
Any other questions? If not, we are at the end of the hour, and thanks, Luna, for a really wonderful talk and great discussion.
Thank you.
Really appreciate you doing this.
Yeah, thank you very much for inviting me, Sarah.
Bye.